Hello and welcome to the next video. We're continuing with the dynamics topic and we're continuing with pretty much revising things we've already done before building on it more. So what we're going to be looking at now is forces, and this bit is going to be quite familiar to you. You've definitely done it in third year. We're just going to be sort of building a foundation to then get harder questions on it, but we need to make sure we've remembered all this base material. So we know what a force is. So forces is push or pull, and they can change three things about an object. A force can change the direction an object is traveling, they can change its shape, and they can change its speed. So you can see in this GIF on the right here, which is very exaggerated. A real golf ball does not quite do this. I think this one was made out of a slightly more rubbery material to sort of really emphasize what's happening. But you can see straight away it's changing the direction. It starts off coming in this direction, then a force happens when it hits that barrier and it ends up coming out in this direction. So it's changed the direction. You can clearly see it changing the shape. It gets really squashed up from round and then wiggles about a bit and wobbles and eventually will go back to being round. And you can see it's changing the speed. It's bouncing back slower than the speed it went in at. And so there are three things a force can change. So let's cover the basics. We know what force is measured in. It's measured in newtons, and we use a capital N for that in our units. Doesn't matter where the force is coming from or what type of force it is, it's measured in newtons. It's measured in newtons because Isaac Newton did a lot of work on forces. Direction is super important in all types of force. You'll see all is highlighted here. So that means force is a vector quantity. Again, doesn't matter what type of force it is, the direction is important. So if you're asked to list scalars or vectors, force is a vector. And in the classroom, one of the ways we use to measure them is a Newton balance. You'll have done an experiment with this in third year, and the force we would have been measuring there was the weight of objects. Remember, we got a bunch of weights and we hung it from that, and so we measured their weight, which was the force due to gravity. Just one example of a force. So what we're going to cover in this video is some of Newton's laws. Now hopefully you remember there are three laws that describe what happens with forces, how they interact and how they behave. And so we're going to look at the first two in this little video, and then we'll move on to the third when we look at some harder examples in the next video. So if we start with the first law, what the first law tells us is that an object will remain at rest unless an external force acts on it. Remember, rest means it's not moving. It's at 0 meters per second. And an object will stay like that unless something happens to it. So unless I push it, or unless you pull it along, or unless something causes it to be thrown up in the air, unless something external happens to it. Or an object going at a constant speed will continue at its constant speed unless an external force acts on it. So if a car is going along at 20 miles an hour, it will keep going at 20 miles an hour unless something external acts on it. And this all comes down to the idea of sort of balanced forces. So there's no real equation for Newton's first law. It's all about the fact that you need a force to make something change, basically. So let's look in a bit more detail then at Newton's first law of motion, and we'll put some examples up here. So if all of these objects are stationary or traveling at a constant speed, what are the missing forces? And so the idea of there being no external force means the forces need to be balanced. So if there's a force pulling something in one direction, there has to be an equal force going in the opposite direction so that the net, the overall force on it, is 0. So let's look at these. And so let's look at this first one here of the helicopter. It's got a force downwards of 98,000 newtons. For this to be at rest or traveling at a constant speed, it needs to have an overall force up and down of 0. So if the force down is 98,000, the force up also needs to be 98,000, and then they'll cancel each other out, and the overall force is that they're balanced. Now let's look at the car. It's got forces going in multiple directions here, so we'll have to balance it in multiple directions. Let's deal with the downwards one. 20,000 newtons downwards, that would be its weight. That's always the force pulling something down. So it must also have a force of 20,000 newtons going upwards. I'm sorry, I should have put newtons on there. If it didn't have the same force of 20,000 newtons going upwards, it would be moving down. It's got 20 newtons going forwards, so if it's going at a constant speed, the forces need to be balanced. So it must also have 20 newtons going backwards. This little ninja down here, it's got 5.6 to one side. If it's at rest, it also has to have 5.6 to this side. And then the wee cat here, if it's got 800 newtons going to the right, it would also have to have 800 going to the left. Now, if it didn't, let's look at this cat for example. If we say it didn't have 800 going to the left and instead it had 500, if we put these forces next to each other, I've got 800 this way and then I've got 500 that way. Well, the overall is actually going to be, well, it's moving this way a bit, isn't it? Because there's a bigger force to the right than the left. And that's when we get into the idea of unbalanced forces. And that's what takes us on to Newton's second law. Before we look at that, we're just going to look at friction. And quite often, friction is one of your forces that's keeping you go at a constant speed or keeping you at rest. So, when two objects come into contact with each other, the force of friction is always present. There are things you can do to reduce it, obviously, but it's pretty much always going to be there. So, friction is a force that stops objects from moving indefinitely. Friction is the reason why if you roll a ball, eventually it will stop. If you throw something in the air, it will slow down and fall to the ground, as well as weight being a thing there. And it always acts in the opposite direction to motion. So if you're driving forwards, friction is acting directly backwards in opposition to where you're going. And the reason we have friction, we know this, but it's because things aren't perfectly smooth. So even if we zoom in here on a sheet of metal, which we'd expect to be perfectly smooth, we can see it's really not. There's loads of little crags and nooks and crannies and things in it. And so here we've got an object on a bench or a table. We can see that in actuality, neither of these objects is smooth. They've all got this jagged pattern. They sort of lock together and stop things moving. Now, if we think on a slightly bigger scale, for example, cars, if you're driving on gravel, it's easy to picture that the gravel is going to cause friction. That's why it's harder to drive on gravel than it is on a tarmac road, because the tarmac road is smoother, so has less friction. It's why, say, Formula 1 tyres, they still have a tread on them, but they're as smooth as possible to just have enough friction so they can take corners and stuff, but to not slow them down and they can go as fast as possible. Whereas, say, off-road vehicles or bikes would have really big treads on their tyres because they might be going up slopes and things where otherwise they would slide. So let's look at Newton's second law then. We've already said that balanced forces mean something is staying at rest or it's moving at a constant speed. So what happens then if we've got an unbalanced force, like in that last example of the cat I talked about? Well, if you apply an unbalanced force, you will change its velocity. It will start going quicker in one direction. And so we have an equation that can go with this, and that equation is F equals ma. And so this little un here under the F, well, that just means unbalanced. So we're saying the unbalanced force is equal to the mass of an object times its acceleration, where as usual, M is the mass in kilograms, A is the acceleration, and F here is the unbalanced force. So if we want to work out how quickly something is accelerating, we need the unbalanced force, that is the overall force acting on it. Obviously, we might need to rearrange that to actually find out the acceleration, and if we did, we'd get this. We'd get the acceleration is equal to the force over the mass. If you want your little triangle for it, it would have F at the top, and then it would have M here and A here. You'll see here we've put unbalanced force here again. You don't need to do that. You won't lose marks in the exam when you're writing down the equation if you don't write that. Just done it here to make it really, really clear that it's the unbalanced force. It's the net overall force that we're using. Basically, if you see an object accelerating, there has to be an unbalanced force. Doesn't matter what that object is, how much it's accelerating, in what direction it's accelerating. If there is an acceleration or a deceleration, there has to be an unbalanced force in action to make that happen. So this is the law that really has an equation that we can do lots of practice with. So let's look at an example of that then. So got a penguin of mass 30 kilograms is sliding along the ice, accelerating at a rate of 0.25 meters per second squared. First, we want to calculate the unbalanced force causing the penguin to slide. And then second, if the penguin is pushing himself along with a force of 10 newtons, what is the friction in that situation? So first, A, we're trying to work out the unbalanced force. So let's start, as always, writing down what we have, what we're trying to find out. So we know the mass is 30 kg, we know the acceleration, and we're trying to work out the unbalanced force. So next, let's write down our equation. We know our equation, that's F equals ma, and we just substitute into it. Nice and simple. We don't even need to rearrange here. So if we do that, we put in 30 for the mass, 0.25 for the acceleration. That gives us a force of 7.5 newtons. Remember, units here. This is a standard 3-mark question. You'd be getting a mark here for the formula, you'd be getting a mark here for subbing in, and a mark here for the answer with units. Right, let's look at B. So B, if a penguin is pushing himself along, what must the friction be? So this type of question, what I'd always suggest you do, just to keep it clear in your head, is draw a quick little diagram like those examples we looked at, showing the forces, just to keep it really clear in your head. Now obviously it doesn't need to be a super detailed diagram, just draw a box instead of a penguin, but if you're on the computer you can get an adorable little gif of a penguin sliding along and do that instead. I mean, this question was worth it just for that. So we know it's going forwards with a force of 10 newtons, so we know there's a force of 10 newtons acting in that direction. We know also that the overall force is 7.5 newtons, so the net force is 7.5. What is the friction going to be? Well, we know the friction has to be acting in this direction because the friction has to be acting opposite his motion. And so this is just like the vectors we looked at in one dimension, because remember, forces are vectors. So we know the overall has to be 7.5. So the friction must go in this direction, and it has to then be the difference between the 10 and the 7.5. It has to be 2.5, because if I've got 10 forward and then 2.5 backwards, my overall is 7.5 forwards. And so that is what our frictional force is, 7.5 newtons in this direction. So hopefully this was very familiar to you. There's nothing here you haven't seen in third year. We haven't gone on to sort of a trickier, harder examples yet. But if you'd forgotten it, hopefully this was a really good reminder and it was all understandable. If not, you know how to get in touch. But But I'm going to set you some examples just like this, and then we'll build on that later in the week. So